Hello, everybody. Welcome back to my YouTube channel. And today we're gonna go through a paper called "Can we solve prompt LLMs for graph learning tasks?" Now, what this paper is about, if you imagine, how do we unify the embedding space between language and graphs, right? It's kind of like the same question of whether we can combine language and images, but in this case, instead of images, we are talking about replacing it with graphs. So are we able to do that? Well, this paper gives us an idea in how to do just that. So they propose an approach called GraphPrompter, which is a way to align graph information with LLMs via soft prompts, right? So, so, so it consists of two components, namely a graph neural network, right? So a graph neural network is a type of neural network that takes in the graph topology and it processes it to give you a prediction output of the graph, right? So, and it also has an LLM, obviously, to process the text data information. And let's go through. Yeah, so this is a fairly short paper. So let's get to the conclusion and let's see what it has to say. Okay, so in conclusion, they found significant potential in LLMs for interpreting graph data through prompt tuning method. All right, so it involves some kind of an adjustment to the prompt and their approach. GraphPrompter is a plug-and-play framework that integrates the capabilities of LLMs with the structural insights of GNNs. In this case, they tested it out on node classification and link prediction in graph data, right? So it uses the GNN for structural insights and it uses the LLM to interpret node-related text data, right? So that's the conclusion, which is pretty much already been covered by the in the abstract. So let's go through the introduction right now. Okay, so obviously, okay, our LLMs have been used in various different domains like images, videos, language modeling, and audio, right? There, and there's a lot of them, but we start to see some of its use case happening in modeling graphs as well. And you can check out some of my previous videos about those applications as well, right? But there is a major challenge in adapting LLMs to graph modality. Namely, it would be some of those inherent discrepancy and mismatches between the text modality and the graph modality, since they are both very different types of data. So, okay, and then listed out some examples here. Existing works primarily map the graph into text while ignoring the irrelevant information and noises in the graphs, right? And they say that this oversight results in insufficient understanding of crucial structural knowledge within the graphs. Okay, and it say furthermore, this problem is amplified when we have large size graphs containing thousands or millions of nodes. And this is pretty common if you are working with like a social network or a GPS map where you have a lot of different nodes and you need to like perform some kind of a graph processing with it. So, and obviously due to the limitation of the context length of the large language models, it is not going to be able to handle millions of nodes, obviously. So, okay, and I believe the paper is trying to somehow solve these issues by using a soft prompt encoded by GNNs for the LLMs to learn to process the graph. Okay, right. And here comes the meat of the framework. So the intuition is this. The GNN is more proficient and in aggregating and transforming information from neighborhood information, which could provide topological information to LLMs. So the idea is to have these GNNs take the entire graph and processes it in order to retrieve that important graph information, and then we can feed those into the LLM. Okay, and it can also guide the LLM in selecting relevant information from the text input and control the generation process of the token generation, right? So in this work, they aim to examine the efficacy, okay, namely the accuracy improvement, right, when using a soft prompt photograph in informing the LLM's prediction. Hence, the question that they are trying to address is, can we soft prompt LLMs? Obviously. So, and I think the answer would be yes, right? If it isn't, this paper wouldn't even come out. But anyway, okay, so they introduce GraphPrompter, right? So GraphPrompter, okay, so it uses frozen LLMs as a feature extractor, right? And and they can avoid fine tuning, right? In parallel, the GNN they use it to produce the node embeddings from the graph, which is then concatenated with the prompt instruction, namely the word embeddings, right? So the node embeddings and the word embeddings are fed into the LLM for learning. So okay, so that's pretty simple. And now let's take a look at the figure, shall we? Okay, so figure one is the the graph prompter for node classification tasks. Okay, so it's only for node classification tasks. Um, the process involves extracting a k-hop subgraph for each node. Okay, so basically what I mean by a k-hop subgraph is it's a local neighborhood of the main node, right? So imagine a local patch, right? So you will have multiple local patches for each different node in the graph, and then you feed those subgraph into the graph neural network, which is then followed by a projection layer, right? So and at the same time, you feed the text data associated with each node into the text embedder, right? They call it the text embedder in this case, all right. And then after that, you concatenate the text embeddings with the node embedding that you get from the GNN in order to create what they call soft prompt in this case. So right here, this and okay, sorry, this entire thing is the soft prompt, right? So extract the k-hop subgraph, feed it into GNN and a projection layer which will be updated, but you keep the text embedder and the large language model frozen intact. But you also have to make sure that you give the textual attributes for the LLM to process as well. So this approach is fairly simple, but it's highly effective, right? So, okay. So let's see if they say anything else about this. Blah, 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 blah. Okay. All right, cool. Right. So let's see. Hold on, just give me 1 second. Sorry, guys, I'm back. Okay. Anyway, right. From what I can tell, it's the mathematical details are pretty straightforward, but I will just go through it quickly. So, okay, right, okay. So in this case, they use a tree hop subgraph, which basically means that three neighboring nodes, right? And that's it. So it's like if you have the main node right here, if I can just draw it right here. Okay, let's say this main node. Then what they meant by tree hop is literally three neighbors, 1, 2, and 3, right? So so essentially it's covering an area of three neighbors, and that's it. And you take this entire graph into and feed it into the GNN, the graph neural network, and that will give you an embedding called the node embedding for each of these subgraphs. Okay, and after that, you would then feed it into a multi-layer perceptron, which is right here called a projection layer to make sure that you can produce the node embedding that aligns well with the vector space of the LLM, right? Which makes sure that the dimension sizes matches with the LLM hidden dimension size as well. So okay, so and I state their rationale here, which I think should be clear. First, they want to use GNN's capability to transform local neighborhood information into meaningful embeddings, right? Because it's designed to be that way. And second, right, to it helps with the integration into the LLM, right? And the LLM can make use of this process node embedding from the graph neural network as a form of soft prompt in conjunction with the usual text data that the LLM gets. All right. And then I think, okay, as for the LLM, right, we first feed in the text attributes for each node, right, into a tokenizer, which then converts those words into tokens, and then you can feed those tokens into an embedder to give you the embeddings of the tokens, right? Such that it can be used by the LLM. And obviously, the final step would be to concatenate both the output from the GNN and the token embeddings by the LLM into a single input, right? Okay, so to mention the intuition is that the LLM can process the semantic content of the text along with the graph embeddings. Right, so essentially we provided two different informations, and we hope that this could help the LLM to make accurate predictions about the graph. So, okay, and then obviously perform experiments like node classification and link prediction, but for now, let's go through the results, right? So as you can see, figure 2 right here, let me change. Node classification experiments comparing the proposed GraphPrompter with baseline approaches. Okay, right. So if we take a close look here, right, the x-axis shows the types of data set and the y-axis shows the accuracy. Okay, figure 2a illustrates a dense semantic setting where both the title and abstract of a paper within the node embeddings, right, while figure 2b illustrates a sparse semantic setting with the title only, so it doesn't have the abstract of the paper. As you can see, right, by using their approach, they get consistent accuracy improvement over the baseline. right? Mhm. And and interestingly enough, the accuracy improvement is actually larger for the dataset called Cora, while for the other ones, it is still there, but it's a bit minute compared to Cora. But I think that's okay. Let's see, do they have any other things? Okay, and yeah, and the fine tuning is done by using low rank adaptation, LoRa, and they use a two A100 GPUs, and they report the mean of 5 independent runs with different seeds. Yeah, okay, this practice is really rare to be found, right? Due to how expensive LM training can be, it is quite impressive that they are able to do this. But then again, the paper is really short. So so I think that's good on their side. Okay, next. Note classification results of their approach with a number of baselines, Cora, blah blah blah, PubMed, archive, products. So they present the average accuracy from 5 independent runs with both title and abstract of the papers provided as input along with specific instructions. Both indicates the best performance, underline indicates the second best performance. Okay, so if you can see right here, obviously, right, their approach scores the best on average, right? Even this one right here, it's the second best in this case. So yeah, so it's literally outperforming like a graph attention network, and also zero shot LLM and soft prompt tuning, fine tuning plus LoRa, right? But as you can see, as you add more of these different components, right, the accuracy starts to improve a lot, and it reaches a peak when once you get the entire prompt system plus you fine tune it with low rank adaptation. So that's what it essentially is in this case, right? Okay. So link prediction tasks. Right. Now let's take a look at link prediction tasks. Okay. Interestingly enough, for link prediction tasks, it is actually performing a bit worse than node prediction tasks. Node classification tasks, right? But just by having the subgraph prompt tuning, it is already performing quite well in majority of the benchmarks. So I say that's a win as well. Okay, and are there anything else? Okay, right. And obviously, if you just straight away just use the LLMs in zero shot approach, right? Just feeding in the input and expecting some kind of an output. Obviously, it's gonna be the worst, right? So that kind of already justifies the need for graph the inherent graph topology information to be inserted into the LLM. That's quite important in this case. So yeah, that's about it really. Yeah. What have we learned? So basically, if you want LLMs to perform well on graph problems, then you really need to get a GNN, right, and make sure that it provides some kind of an input into the LLM, and that will ensure you to get some kind of a good accuracy outcome from the LLM. And obviously, there are like different approaches. Some even propose to use just the LLM part without the GNN part. but I have covered that in my previous video. So if you want to learn about that, go check that one out. But for now, if you like this video, make sure to like and subscribe and comment down below if you have any questions, and I will catch you all in the next one. Bye.